I want to welcome you all to a new video lecture series that we are going to start today. And in this video lecture series, we will look at the modeling, analysis, and design of a multi-storied office building in ETABS according to the Nepal National Building Code 105-2020. In this video lecture series, we will look at the design of a 8-story office building which has one basement and remaining 7 stories. And our design will be based on the Nepal National Building Code, the updated Nepal National Building Code 105-2020. Before beginning with the design in ETABS, in our first lecture today, we will look at the introduction to NBC 105-2020 and then compare it with IS 1893 Part 1 2016. So let's begin with today's lecture. So the updated version of this NBC 105 code, which is the code for seismic design of buildings in Nepal, this was approved by the Council of Ministers on 2077 Shravan 19, and the code was published in Nepal Gazette on 2077 Mangsir 8. The first version of this code was published in 1994. After its publication, this is the first revision of that particular code. And the objective of this standard is to provide designers with general procedures and criteria for the structural design of buildings prevalent in the Federal Republic of Nepal, considering the seismicity in the parts of the country. This objective is stated in the foreword or in the introduction of the code itself. Let us first look at the principal modifications from the Nepal National Building Code of 1994 when comparing it with the updated version of 2020. The first is that the performance requirements are defined precisely in terms of collapse prevention and damage limitation. There is a further recommendation to verify the performance requirement, checking the ultimate limit state and serviceability limit state. So what two major principles of the earthquake resistant design of any building is that first, under moderate shaking, I have already talked about these basic principles in our first video lecture regarding design of RCC residential building according to IS code also. I want to state those two principles again. First is that under moderate conditions or under moderate shaking during earthquake, the structural elements of the buildings are not affected or there is no damage in the structural elements, and there can be moderate to heavy damage in non-structural elements, but there should be no damage in structural elements. And the second principle is that even when there is damage to the structural elements, the structure should not totally collapse so that we can perform the evacuation of people from those buildings. That means the structure should guarantee life safety. So our first principle, which says that the structural elements should not be affected during moderate shaking, that is related to the serviceability limit state. And the second principle, which prohibits the total collapse of building, is related to the ultimate limit state. So the modifications in the present updated code says that, or it precisely defines the performance requirements in terms of both serviceability limit state and ultimate limit state. Second point, nonlinear methods of analysis have been introduced, retaining the linear analysis as in the earlier version. If you are used to designing any building using the previous code of 1994, then you can see that various nonlinear methods of analysis have been introduced, which was not introduced in the previous version or in the older version. The load combinations for parallel systems and for non-parallel systems have been revised with changes in load factors. Parallel system means all the force resisting elements or all the deflection resisting elements are oriented in two mutually perpendicular directions. Those are the parallel systems. For example, suppose that, let me draw here, if this is our building and if these beams and columns are present in horizontal grids, and if there are any shear walls, then if those shear walls are also oriented along these two perpendicular directions, x and y, then we call that parallel system. In contrast, for example, if we have this kind of building plan here in which one column is out of grid, for example, if one column is situated here, or if orientation of column is different from the orientation of other columns in this structure, or if the shear wall is somewhat like this, not parallel to this x and y axis, then we call this non-parallel system. Load combinations have been revised using different load factors for both of these types of systems. Fourth point, the earthquake levels considered in this code are according to two earthquake levels. One is having a 475 years of return period, and the second is having 2475 years of return period. All of these principal modifications that I am describing now, it is extracted from the code itself. If you download this version of the code and see, you can also find these exact same points. Fifth number, the spectral shape factor for the equivalent static method and for the modal response spectrum method are different, and the response spectra are specified for 4 types of soil types. So our code, based on the value of different factors, classifies the soil into 4 types, A, B, C, and D. And for these different 4 types, the spectral shape factors have been simultaneously defined for both equivalent static method, which is a linear static method, and then the modal response spectrum method, which is a linear dynamic method. So type A means stiff and hard soil, type B means medium soil, type C means soft soil. And for structures which are being constructed in Kathmandu Valley and some municipalities around the Kathmandu metropolitan city, we have type D, which represents a very soft soil. The seismic zone map of Nepal has been revised based on the recently carried out probabilistic seismic hazard analysis. Accordingly, the zone factors for major cities and municipalities have been changed. If you remember, we considered zone factor Z also during the design of building based on IS code. Now, different zone factors have been prescribed for different cities, and for those cities for which zone factors have not been defined, our latest revised NBC code presents a map of Nepal with different zone factors for different areas. So the zone factor has also been revised according to the recently carried out seismic hazard analysis. The importance classes and importance factors have been revised. We also learned about importance factor in our previous course. The empirical formulae for determination of fundamental translation period have been revised. We will see about this calculation of time period during our design classes. The horizontal base shear coefficient will be determined separately for ultimate limit state and serviceability limit state. In our upcoming slides, we will see about the horizontal base shear coefficient calculation from both perspectives, from Nepal National Building Code and also from Indian Code. We will make some comparisons there. And these coefficients are expressed in terms of ductility factor and overstrength factor. This ductility and overstrength have been represented by a single factor, that is response reduction factor in Indian Code. In Nepali National Code now, there are 2 separate factors, ductility and overstrength, based on the structural system that we are going to use in our building. And these ductility factors and overstrength factor replace the performance factor K in the earlier version. If you remember formula in our previous version of 1994, then you can remember that our horizontal base shear coefficient was given by this formula CZIK, where this K was the performance factor. Now this formula has been changed in this present code, and also this K performance factor has been replaced by ductility factor and overstrength factor. The horizontal design spectrum for the modal response spectrum method has been given different for ultimate limit state and for serviceability limit state. And the clauses on the parts and components of the building have been revised. This is our last modification. Again, all of these modifications from 7 to 11 have also been extracted from the same code, that is NBC 105 2020. So what are the contents in NBC code? You can see here 1 to 10. There are 10 parts or 10 chapters in our updated code, and there are 2 annex added. These 2 annex were not present in our previous version of the code. Now 2 annex have been added regarding design and detailing of RCC structures and steel structures for earthquake loads, and other 10 parts include the following things that you can see on your screen right now: title, scope, definition, and notations. This first part is present in almost every code. General principles, scope of analysis, seismic hazard, dynamic characteristics of structures. And finally, if you see here, we said in our previous slide that this present code gives us with the linear as well as non-linear analysis method. You can see from part 6 to 9, equivalent static method, modal response spectrum method, elastic time history method, non-linear static and dynamic analysis. These 6 to 9 means these are different analysis methods or analysis types. And finally, in number 10, we have parts and components. So these are the contents of NBC 105 2020. I would like to say this: the new building code. Let us say the 1994 version is the old code and 2020 version is the new code. Now let us see some basic clauses or some important clauses that are included in the new Nepal National Building Code, and let's see some comparisons with the corresponding clauses in IS 1893 Part 1 2016. Before beginning with this part, what I would like to say is that what we have to understand is that this Nepal National Building Code 105 2020, it is not any concrete design code or any steel design code. Similar to what we have in case of the Indian code, for example, we have IS 800 for structural steel design, whereas IS 456 for RCC design. This NBC 105 is not equivalent to those two codes, that is for steel design or concrete design. Designing our building on the basis of Nepal National Building Code means that we are calculating the earthquake loads based on this code. Otherwise, after the calculation of earthquake load, when we actually design different RCC components or different steel components, then those design will be based on the IS code, because we do not have particular steel design code or concrete design code in case of Nepal. We only are using this NBC 105 to calculate the earthquake loads, to do seismic hazard assessment. That you have to remember. So let's start with the scope here. What NBC 105 says in clause 1.2 is that it is applicable to all buildings, low to high-rise buildings in general, and this is applicable to buildings made of reinforced concrete, structural steel, steel concrete composite, timber, masonry. And this code is not applicable to base isolated buildings and buildings equipped and treated with structural control. That means, for example, if we have viscous dampers present in our building, that is a special method of structural control, and the buildings having those dampers cannot be analyzed using this NBC 105. For that, we have to use international codes. Whereas our IS 1893 Part 1 2016, the name of this code is Criteria for Earthquake Resistant Design of Structures Part 1, General Provisions and Buildings. So this IS 1893 code, this standard primarily deals with earthquake hazard assessment for earthquake resistant design of buildings. So not only buildings, we can use this IS 1893 code to calculate loads for other structures except buildings also. For example, liquid retaining structures such as underground water tank or overhead tanks, bridges, embankment and retaining walls, industrial and stack-like structures, concrete, masonry and earthen dams. So except building or beside building, the scope of this code is also for other structures. And this IS 1893 code, it is also applicable to critical and special structures like nuclear power plants, petroleum refinery plants and large dams. We may need to use or we may need to take help of specialist literature for these critical structures, but besides that, the general provisions of IS 1893 Part 1 can also be used for these critical and special structures. So this is the difference in the scope of the two codes. Let's go to another slide. Let's see here now. The most common method that we use for the analysis of our regular buildings is the equivalent static method. So in which case can the equivalent static method be used? According to this clause 3.2.1 of the new Nepal National Building Code, what it says is that the equivalent static method may be used when at least one of the following criteria is satisfied. So we have three criteria here. For example, number one is the height of the structure is less than or equal to 15 meter. The natural time period of the structure is less than 0.5 seconds, and the structure is not categorized as irregular is for 5.5. This means the clause number 5.5 of the same code, and the height is less than 40 meter. So when any of these three clauses is satisfied, then we can use the equivalent static method. And the same case for IS 1893 code is that, first let's see, this first clause is related with the height of the structure, and NBC says that if the height is less than 15 meter, we can use this static method. Same is the case for IS 1893. In clause 7.6, it says that the equivalent static method shall be applicable for regular buildings with height less than 15 meter in seismic zone 2. So besides having height less than 15 meter, we should also ensure that the structure is located in seismic zone 2. If it is located in other seismic zones, for example 3, 4 and 5, which have higher seismic hazard, then equivalent static method is not sufficient. We also have to go for dynamic method or non-linear methods also. But for buildings height less than 15 meter in seismic zone 2, ESM or equivalent static method can be used. Similarly, if the structural time period is less than 0.5 seconds, then according to the new code, new National Building Code of Nepal, we can use the equivalent static method. In case of IS code, what it says in this clause is that if the natural time period of regular structures is less than 0.4 seconds, then we can use equivalent static method. So the difference is 0.5 here and 0.4 here. And when to use response spectrum method, the modal response spectrum method may be used for all types of structures where ESM is not applicable. A three-dimensional analysis shall be performed for torsionally sensitive structures. For all types of structures these days, we do three-dimensional analysis because of the availability of our structural design programs. When these programs were not built or when there were no such programs, then doing a three-dimensional analysis would be very complex. So in those days or in those cases, only two-dimensional analysis were performed. But after the advent of these structural analysis softwares, then three-dimensional analysis is performed for all types of buildings. Now let's go to here load combinations. What we see in load combinations, first, there is one change in the new National Building Code as compared to the old building code in case of load combinations and this load factor. If you remember, when performing design according to IS code, when defining mass source, what we did was that if the live load was less than or equal to 3 kilonewton per meter square, then we considered only 25% of that live load. We supposed that only 25% of those live loads would participate in vibration during any earthquake shaking. But if the live load was greater than 3 kilonewton per meter square, then we considered 50% of that live load. Now, there is no such thing as less than or equal to or greater than 3 in the new National Building Code of Nepal. What it says is that the load combination shall be this. First is 1.2 dead load plus 1.5 live load. This is the first load combination. And if you see here the second load combination, it is dead load plus lambda times live load plus minus earthquake load. So this lambda value, the load factor, this is lambda is the load factor, and this load factor lambda value will be 0.6 for storage facilities and 0.3 for other uses. So what it means is that when we are assigning live loads in our building according to this new code, we have to separate. We have to make two cases for load patterns. One will be the normal live load, which has load factor of 0.3. And if we have, for example, any room separated for storage of our different components or storage of different things, then for that kind of live load, we have to use the load factor of 0.6. We will go into detail about this load factor during our design classes. Whereas in Indian code, we have these load combinations here. 1.5 dead load plus imposed load. Imposed load IL means live load. 1.2 dead load plus imposed load plus minus earthquake load. 1.5 dead load plus minus earthquake load, and 0.9 dead load plus minus 1.5 earthquake load. So these are the load combinations. And remember that these load combinations are for parallel systems. Parallel and non-parallel systems I talked about in our previous slides. So this load combination here for the Nepal National Building Code and this load combination here for Indian code, these are for parallel systems. But for non-parallel systems, that means when lateral load resisting elements are not oriented along mutually orthogonal horizontal directions. You can see about these in clause 7.1 and table 5e in Indian code also. In case of such non-parallel systems, what we should do is that when defining the load combinations, we should design our buildings for the full earthquake load plus 30% of earthquake load in another direction also. For example, if you see here, this first load combination here has no earthquake load component, so it will be the same. Now the second combination here, we have plus minus earthquake load. So if it were a parallel systems, then this E here would be either earthquake load in X direction or earthquake load in Y direction. But for non-parallel systems, what we will do is that first we will consider earthquake load EX plus minus 30% of earthquake load in EY direction or Y direction, that is 0.3 EY. And when we are designing for earthquake load in Y direction, similarly we will do 30% of earthquake load in X direction, EX, plus minus full earthquake load in Y direction, that is EY. So this is the difference here. Similar is the case in case of Indian code also. What Indian code in clause 6.3.2.2 says is that in these four load combinations, wherever there is earthquake load component, that earthquake load component should be replaced by this, either plus minus ELX plus minus 0.3 ELY, that means full earthquake load in X direction and 30% of earthquake load in Y direction, and plus minus 0.3 ELX plus ELY, that means full earthquake load in Y direction and 30% of earthquake load in X direction. So we are designing for higher earthquake load in case of non-parallel systems. So this is about load combinations. Now we come to the important part, that is horizontal seismic base shear calculations. So this is somewhat a tedious process here. While designing, I will provide you with, or we will use Excel sheet for the calculation of these horizontal seismic base shear. But first, let's see how it is calculated. I will just go through this, and if there is anything to explain, I will explain it here. If you do not understand, do not worry. We will again come to these clauses during the design classes also. So let's see here first what our NBC code in 6.2 says is that the horizontal seismic base shear V acting at the base of the structure in the direction being considered shall be calculated as CD, which is a function of T1 into W. So before going further, if you have any problem regarding the theoretical explanation of some of these terms or explanation of some of these concepts regarding horizontal seismic base shear coefficient or any other acceleration coefficient or what is base shear itself, then I would like to request you all to go to our YouTube channel and see there our playlist for the design of RCC residential structure based on Indian code. That is, I suppose, one of the most important lectures in our channel in YouTube, because I have explained in detail regarding various theoretical concepts. Besides the modeling and analysis and ETABS, I have discussed with different theoretical bases. So before starting this series, I would like to request you all to go through that series first. Then many things will be clear in this series also. So coming back to this, we have base shear formula is CD T1 into W, where CD T1 is the horizontal base shear coefficient that is defined in clause 6.1, and W is the seismic weight of the structure as per clause 5.2. As you are used to with the design on the basis of this code, then many of these you can also remember by heart, and you don't have to go through these codes again and again. So let's see first how to calculate CDT1. This V is the base shear, CDT1 is the horizontal base shear coefficient, and W is the seismic weight. So how to calculate CDT1? So for ultimate limit state, in clause 6.1.1, the value of CDT1 is given for ultimate limit state. Remember, you have to calculate these CDT1 for both ultimate limit state and serviceability limit state. So for ultimate limit state, CDT1 is given as CT1 divided by R mu into ohm mu. So what are these factors? CT1 is the elastic site spectra, which is again defined in 4.1.1. R mu is the ductility factor, and ohm mu is the overstrength factor. We talked about this. These factors represent our response modification factor. So when you have got the value of these three factors, you can calculate CDT1. And for serviceability limit state, our formula is CST1. Now CST1. Look here, we had CT1 here, and we had CST1, and then again ohm S. That means our overstrength factor for serviceability limit state, and CST1 is the elastic site spectra determined for serviceability limit state as per 4.2. So base shear CDT1 into W. CDT1 is calculated separately for ultimate limit state and serviceability limit state. These are the formulas, and CDT1 for ultimate limit state is this, CDT1 for serviceability limit state is this. Now this CST1 that you see here, this CST1 is determined from 4.2, and 4.2 says that CST1 is 0.20 into CT, where CT is the elastic site spectra for horizontal loading determined from 4.1.1. So whatever CT value that you use for ultimate limit state here, if you multiply that by 0.20, then you get CST, and this CST is used for base shear coefficient calculation for SLS, that is serviceability limit state. So we got the value of CST1 here, and the value of CST1 and both CT1 is dependent on CT. Now from where to calculate CT? From 4.1.1. In 4.1.1 we have CT as again CST into ZI. CST is the spectral shape factor, which is determined from 4.1.2. Z is the seismic zoning factor given in 4.1.4, and I is the importance factor given in 4.1.5. So there are many symbols here. Do not get confused. If you go through slowly by yourself also, you will get the value of these symbols and the meaning of these symbols. So last thing we needed to find was CT, and CT is dependent upon this spectral shape factor CST and ZI. This spectral shape factor is dependent on the swell type that we said earlier. Our new building code divides swell type into 4 categories A, B, C, D, and this value of spectral shape factor is dependent on this swell type and the time period. We have this spectral shape factor diagram for equivalent static method and response spectrum method separately. So if you are determining the value of CST for equivalent static method, you have to look at figure 4.1. And if you are designing using a response spectrum method, then you can use either figure 4.2 or you can use the formula that is given here. this 1 plus alpha minus 1 into T by TA if T is less than TA, alpha if TA is less than or equal to T, but T is less than or equal to Tc, and this another formula for if T is greater than or equal to Tc and less than or equal to 6. This formula is for response spectrum method and also for nonlinear time history analysis, vertical loading, and parts and components. So value of these various parameters alpha, Ta, Tc, K is present in table 4.1 here. I will not go through in detail about these values now. When we perform response spectrum analysis, then I will go through these values once again and how we perform the calculations. And finally, we have empirical formula for determination of time period here, which is given as kt into s to the power 3 by 4. H is the height of the building from foundation or from top of a rigid basement, and value of kt is different for different types of framing systems. For example, for moment resisting concrete frame, which we will be using for this design, is 0.075. For moment resisting structural steel frame, it is 0.085, and similarly other values for other structural systems. So 5.1.2 gives us the time period. And then we have zoning factor, and then we have importance factor. So let me go from backwards what we did. First, we find the time period of our structure by this empirical formula. And based on this time period and the swell type, we calculate this spectral shape factor CST, which is separate for response spectrum method and for equivalent static method. And after we calculate this CST value, we use the value of CST, zone factor, and importance factor to get this elastic site spectra CT. And this CT value is used to get this CDT1 value for ultimate limit state and serviceability limit state. You use CT value directly here for ultimate limit state, and for serviceability limit state you will calculate CST1, which is 20% of CT. And these ductility factor and overstrength factor you look from the tables given in the code. After finding this CDT1 value, you calculate the base shear for the direction considered using this formula CDT1 into W seismic weight. We will come to this seismic weight calculation a little bit later. Now we have got the value of all these symbols here. Finally, you can calculate the base shear. So this is about calculation of base shear in NBC 2020. So let's look here in clause 4.1.4. we have our seismic zoning factor, and table 4.5 gives the seismic zone factor for different cities or municipalities. For example, if you look here Kathmandu, you have PGA of 0.35. Similarly, other major cities are given here. And if you do not have your city here in this table, you can look at the seismic zoning map of Nepal in figure 4.3, and you can interpolate for different values of zone factors according to the place in which you are constructing your building. So this is seismic zoning factor. Similarly, importance classes and importance factor are given in 4.6. For the least important among these three classes is the class 1, which is for ordinary structures. That means all those structures except falling in classes 2 and 3, you have importance factor 1. And for school, colleges, cinemas, assembly buildings, temples, police station, and other types of structures, you can look here. The importance factor is 1.25. So what it says is offices and residential quarters for senior personnel required for rescue and relief operations, and any other buildings designed to accommodate more than 500 persons. And finally, the structures with the highest importance is these hospital, fire station, police headquarters, power station, structures for support or containment of dangerous substances. All of these critical and special structures, you have the importance factor is 1.5. And remember what our code says is that importance factor for 1.5 shall be applied if the facilities listed in importance class 2 are to be used as a shelter in case of a disaster. For example, if our schools, generally what happens is that our schools, colleges, these are used or these are to be used immediately after a disaster because of the open spaces or Because of the importance of those structures, this can be used as shelter immediately after a disaster, and that disaster can be anything such as earthquake, fire, or any other hazard. And if these structures in class 2 are to be designed or are to be used as a shelter in case of a disaster, then importance factor should be changed from 1.25 to 1.5. So take care of this also. And we talked about ductility and overstrength factor. I'm not going into this theoretical part. Let's see here. We have a lecture in response spectrum analysis lecture series. I think it is the first video of that series in which I have talked in detail about response reduction factor. So please go through that if you do not understand these concepts. I will post a link of that video lecture below this video also. Table 5.2 gives us ductility and overstrength factor. So this is for ultimate limit state and this is for serviceability limit state for different structural systems. It may be concrete, composite, or steel structures. There are 21 different structural systems here. So you can get the value of this ductility and overstrength factor from table 5.2. And finally, seismic weight. We talked about live storage and other normal storage in our previous slide. In Indian code, what it says is that if our live load is less than or equal to 3 kilonewton per meter square, we will take 25% of that live load during calculation of seismic weight. If the live load is greater than 3 kilonewton per meter square, we will consider 50% of that live load. And if it is our roof live load or the live load acting on the roof, then we suppose that that roof live load does not act in the calculation of seismic weight and we take the factor 0 for roof live load. And for all other dead loads, we consider that 100% of those dead loads are incorporated while calculating seismic weight and we take the factor 1. Now in case of our NBC code, there is no such thing as less than, greater than or equal to 3. What it says is that if the live load is regarding storage, then factor should be 0.60, similar to this load factor for load combinations. For other purpose live load category, 0.3, and roof live load, we do not need to consider roof live load for seismic weight calculation and we consider it 0 or nil. So this is how you calculate seismic weight. So that was about calculation of horizontal base shear coefficient and base shear in case of the new code or new Nepal National Building Code. For the horizontal seismic base shear calculation according to Indian code, I'm not going to go through in detail. I've already discussed it in our previous lectures. It is given in 7.2.1 where the base shear is given as AH into W. W is the seismic load and is calculated as 7.4. See here in table 10 we have for live load or for imposed load up to and including 3 percentage we take is 25% and above 3 50%. And this AH here is the design horizontal seismic coefficient calculated as this formula Z by 2 SA by G R by I. Z is the zone factor you can find in table 3 of the Indian code. I is the importance factor which is 1.5 for critical and lifeline structures, 1.2 for business continuity structures and 1 for the rest. In Nepal Building Code we had 1, 1.25 and 1.5. R is the response reduction factor given in IS 1893 part 1 to 5 for the corresponding structures. You can also find these values in the same code. This R is equivalent to our ductility factor and overstrength factor in Nepal National Building Code. SA by G is the design acceleration coefficient for different soil types corresponding to natural time period of the structure. In our Nepal National Building Code, instead of SA by G, we had this CHT, which is the spectral shape factor. Now we have SA by G, which is again different for equivalent static method and dynamic method. But similar to what we have in our Nepal Building Code, again this SA by G value is dependent upon the soil type and the time period of our structures. So A gives us SA by G for equivalent static method and B gives us SA by G value for response spectrum method, and you can see these values in both cases are dependent upon T, which is the time period, and for different soil types. The soil types, we have 3 classes in the Indian code, whereas we had 4 classes in the Nepali code. So this is about horizontal seismic base shear calculation in case of Indian code. And finally, we have effective stiffness of cracked sections. In our previous Nepal National Building Code of 1994, I think there was no any codal provisions regarding the effective stiffness of different components, but in our updated code, these have been included. What happens is that during earthquake shaking, cracks develop in different structural components. So, because of the formation of those cracks, the stiffness of those elements decreases. And to simulate what is happening in the real structures, we reduce the stiffness of those cracked sections by using this effective stiffness for different components. In beam, we take 35% for flexure and 40% for shear, columns 70% and 40% for shear, 70% for flexure. This is the same as in IS code, which says that in clause this 6.4.3.1, in reinforced concrete and masonry structures, the moment of inertia shall be taken as 70% of gross moment of inertia for columns, which we have here 70, and 35% of gross moment of inertia of beams, which we have 35% here. And for steel structures, we consider the gross stiffness value. We do not apply any stiffness modifiers. So this is about the effective stiffness of cracked sections. We will apply these stiffness values or these factor values in our design classes also. An interstory deflection, once we have completed the analysis of our structure, then we have to check for different factors in our structure, and one of them is the drift or interstory deflections. NBC clause says that the ratio of the interstory deflection to the corresponding story height shall not exceed 0.0258 ultimate limit state and 0.006 serviceability limit state. In IS code, we have story drift in any story shall not exceed 0.004 times the story height under the action of design base shear with no load factors mentioned in 6.3. So this is the difference of values here. You can see here. This is about interstory deflection, and this completes our introductory slides on this new design lecture series. So I hope you have been acquainted with some interesting codal provisions in the new National Building Code of Nepal and its comparison with the corresponding codal provisions in the Indian IS 1893 Part 1 code. So in this lecture series, we will be focused on the National Building Code of Nepal for the calculation of earthquake loads, and then we will perform, finally after analysis, we will perform the design of our structural elements based on the concrete design code, that is IS 456 of Indian code. So if you want to or you have to study in detail about the code, so download the Nepal National Building Code from the internet, and if you go from the beginning to the end of the code, then you can be acquainted with other codal provisions also, and it will make you clear about this codal standard that has been recently updated. And as I said earlier, 2 annexes have been added in the new updated Nepal National Building Code, and those annexes are about the design and detailing of reinforced concrete structures and steel structures. You can go through these annexes also. So that's all for the introductory classes that we have started today, the introduction to NBC 105-2020 and comparison with IS 1893 Part 1. In our next lecture, we will see the plan and elevations of the building that we are going to design, and then we will start with modeling in ETABS. So we'll meet again soon. Thank you.